All right, let's get started. There's a couple announcements I posted. We've got a student who wants to go to the National Society for Black Engineers Convention. We've not sent students this to before, but we want to send a couple students maybe this year in Atlanta, Georgia. We have some funding in our department that could cover the registration and the airfare, but students would have to cover their own food and lodging for this. So if you're interested in this, let me know. The other thing is a week from tomorrow is Community Day, and some of you have probably already signed up for a Community Day activity, and that's great. But if you're not, and you want to hang around with computer people doing fun stuff, or at least doing stuff, I'm leading a small group to the Makerspace, which is in West Duluth. We're going to be cleaning up there. Give us a chance to, at least see they have these wood CNC machines that are run by computers. They have laser cutters, 3D printers, things like that there. And we'll just be cleaning and organizing the Makerspace, some of the staff there. So if you're interested in doing that, there's a little sign-up sheet, and I hope to do it. Probably won't spend, I'd like to spend just a couple hours there. So I was thinking 10 till noon. So we'll probably get there at 10, work there for a couple hours, have pizza there, and then wrap up. So do a little community service but be done, by noon or 12:30, something like that. However long it takes to eat pizza for that. So that's what I'm kind of thinking. So sign up if you can. It's nice to that it gives you a wonderful chance to spend time with your professors outside the classroom, and you're thinking, boy, that sounds like just a wonderful morning that I want to do there. So I've been trying to teach myself how to use the lathe to make bowls at the Makerspace. So maybe I'll show you a bowl that I've been making or something like that. Okay, so that's our two announcements. Let's jump into Unit 6. So we started doing convolutional neural networks last week, and we got into the basics of them, setting up these layers, talking about a convolutional layer, which applies a filter here, and then a pooling layer, often a max pooling layer, where we'll take a bigger image and pool it down, shrink it down to half its size there by just checking for what features are in each of these 2x2 squares for that, combining those together and eventually feeding those into some dense layers of a traditional neural network. And we're working with networks that we were defining and we were training from scratch that had maybe a dozen layers to them, which is a good start. And we could train them, and training would just take a short amount of time here, maybe 10 minutes or so. Now we're going to get into deeper stuff here. I'm going to go over this first learning resource on deeper CNNs and transfer learning. And then we're going to do an activity. Sorry, I get tired of talking to you. So we're going to do a learning activity for the next, the learning APIs and the bounding boxes and that sort of. So these two things, we're going to do that. And if we have time, I'll talk about about the writing again a little bit here. So we'll do these, try to get through these learning activities. Like I say, I'll go through the first one and we'll have an activity here. We'll let you work on some of these other ones here. Normal stuff for the rest of it. We have an explore activity here that is to explore some stuff. We have our discussion here. We're going to be posting our results to the discussion thread and then talking about resources for pre-trained or pre-built systems on the second part of the thread. And we'll do a learning notebook, and then we'll do the project. And so we'll go over these on Thursday. The learning notebook isn't that bad, so it should just take like half the class on Thursday to go through that. I think, although training, we might just have to let it sit and train for a while. And then the project, hopefully we'll dive in. There's 2 different Kaggle challenges that we've modified so we can kind of do them in class for them here. Okay, so let's jump into this first one and start talking about deeper CNNs for these. So there was this, which was at one point thought to be an impossible challenge, the ImageNet Large Scale Visual Recognition Challenge for this. And they had a very complex challenge with some images for it and evaluating it, where they are trying to get the computer to classify some objects in these papers or in these images for them. And so this was a huge challenge. A lot of people wrote, researchers would write papers, would try different things and write papers and then show their results and try to compete in this challenge in different ways. So this kind of drove the research around 10 years ago here. And the first convolutional neural network made waves because it won the challenge back in 2012, the second year of this challenge. And it is similar to what we've been doing here. We had some convolutional layers. Let me open this up in a new tab. So it had some convolutional layers, a pooling layer, another convolutional layer, a pooling layer, 2 convolutional layers, a pooling layer, and then 3 layers of fully connected versions. And the outputs for categorization is or classification, almost always what we call a softmax layer here. And again, they are trying different things. So the initial ones were, well, these ones were 3x3 convolutional layers. And again, they had 384 filters, so lots of filters here. The beginning was an 11x11 filter, which we don't see anymore. And then it fed into a 5x5 filter of 256. So again, some different structures there, but a relatively small. But that AlexNet won the competition. It had 60 million parameters for us here. Jump to 2014, 2 years later, we had VGG 16 and VGG 19, which jumped up the accuracy quite a bit. They kind of standardized some of the ways of doing things. So they did a lot of they just did 3x3 filters here. They started with 64 features. After pooling, they jumped up to 128. After pooling, they jumped to 256. After pooling, they jumped up to 512, and they stayed at 512. All of these had these huge dense layers at the end. 4,000 layers connected to 4,000 layers. I mean, yeah, nodes connected to 1,000 nodes, and then the softmax at the end here for this. And VGG 19 and 16 were very similar. VGG 19 just had 19 letters. VGG 16 had 16 layers. So again, getting up there for this, more layers, but still kind of in our standard approach to things. But we were getting up to 138 million parameters, 140 million parameters. Again, we've trained VGG on a desktop computer on the whale data. And it'll take about 3 days to train VGG 16 on the whale data. For the project, I've taken the whale data and cut it down a lot, so that rather than having 1,000 whales, you have, I think, 100 whales. So it's 10 times less than the original challenge, just so you know. But it's still going to take us a while to train this here. we are also beginning to ask lots of questions like, is this the best way to set these things up? And can we connect these in different ways? People were trying different numbers of convolutional, 5x5, 3x3s. Is sequential the right way to do this here? And so that led us into Google. From Google, we had the inception layer. And it's interesting, you can see like inception from AlexNet, from 60 million parameters, we went on to 5 million. And from like VGG's 144, we went down to just 11 million. So often a factor of 10 times less parameters or connections with similar or better results here. So what did the inception stuff do? So I'm going to bring up this article and talk a little bit about what inception did. So again, here's our AlexNet training. And again, this is the type of things that it's training on in ImageNet. So we have these images of container ships and mushrooms and leopard, and all these things for this. VGG 16 training. But let's get down here to GoogleNet or Inception. So Inception created this unique kind of combination. So rather than taking a layer, going through a 3x3 convolution and going out, they had a layer go feed to 4 different layers here. And then those 4 different layers were all combined into one output. So they had a 3x3 convolutional layer, a 1x1 convolutional layer, a 5x5 convolutional layer, and a 3x3 max pooling layer. And all that was concatenated or combined into one output. So this was called an inception model here, and they can define that in code. In fact, we'll see code that will define these layers. I think in the project, we can look at examples of this. That was Inception 1. Inception 2 went to this one, where they learned the benefit of doing 1x1 convolutional layers. So they would do a 1x1 convolutional layer, feed that into a 3x3 convolutional layer, and then concatenate it. So they did, this was the next layer of Inception. And then they would build these modules up. So you can see each of these layers is actually a Inception 2 layer, where it divides, sends the input multiple places, has 2 layers, and then combines them. So these are the Inception layers. And so each one, 1, 2, 3, 4, 5, 6, 7, 8, 9. They had 9 Inception layers here for it. Well, one of the problems with this is that it's getting so big. So 9 layers, but each layer has 3 different sublayers. So that's getting up to almost 30 this had over 30 layers to it. And then the back propagation, the training was getting long. So what they tried to do is output things along the way, projections along the way, so that these would all be trained, and we try to get some training to go into this at different points. Now, this output along the way hasn't necessarily caught on so much, but it's one way we're trying to get the training to go through all these layers for this. But you can start seeing how complicated here. And so in order to do this, you need lots to manage all these parameters. You need lots of data here. And ImageNet had a lot of these features about it. So again, this is trying to show kind of the detailed structure of how this is good. And again, they're training attempts. And this is about 10 years ago we were trying to do this sort of stuff for this. Okay, so we had these inception layers that we were setting up. Oh yeah, and here's the code for these. Now, so far, when we've been defining code, we always do it sequential. So we have a little sequential network definition at the top, and then we just say each layer, we just list the layer, and we assume that it's connected to the layer above it, and its output goes to the layer below. It's all sequential. For inception, we can't do that. So when we define a layer like this, we have to specify where it's getting its input. So that means we have to name every layer. So every layer is given a name here, and then we use those names later on. So we'll have this layer named pool 1 here. And then later on, we'll say that this will get it from pool 1 here. So again, it's a little more complicated. And again, we won't really go into this because it's a little bit more than I want to for this class. But again, if you define this stuff, you'll see that every layer is given a name. And then we say where the input is coming from for all of these layers here. So, okay. So inception was one way. The other thing about 2015 we learned to do was what is called residue networks. And this introduced this idea of a skip connection. So what we would do is we'd have our 3x3 filters. We'd have maybe 2 or 3 layers of those, but we'd also have a connection that would skip over those. And what that wouldn't necessarily help that much with the training, but would help often with the error corrections, in that when we're propagating errors backwards, our errors could kind of skip over some of this stuff here. And this, with these larger networks, we're able to do some skipping over some of these ideas here for this. Okay, so then let's look at how we might define some bigger networks here. So again, we didn't have any real good rules, but we were working on some guidelines. So if we had some basic network, we could look at trying some things, scaling it wider so you have more filters at each level, doing it deeper so you'd have more layers here, or working with the resolution. So we're maybe working with higher resolution images here. And this shows kind of the growth of these networks. The size of these networks, the size of the circle shows how many parameters these networks had here. And then how accurate they were doing. And one thing we're finding is that the bigger the network often, increasing network size or depth often helped here. And the amount of training that went into these networks helped to get better accuracy. So over time, we are slowly building on these. So what we tended to see would be, VGG 13 leading to VGG 16, leading to VGG 19, ResNet 18, reading with, ResNet with 18 layers, going to ResNet with 34 layers, going to ResNet with 101 layers, going to ResNet with 152 layers. And each step up required more training, but got us better accuracy on these results. So this kind of shows this growth. The first convolutional network, AlexNet, Inception v3 here, and moving up. So our accuracy over time. So by 5 years ago, we were, EfficientNet here was one of our top ones, and we're getting accuracy on the ImageNet database of 90%, which no one ever thought was possible. So, skip over some, let's see. And again, we tried different types of layers and training here. One thing we learned is that training took a long time on these things, but we could reuse the training some. So we often train these networks on these ImageNet databases, but we found that we could then use these networks trained here in other areas for that. So again, this tries to show the training stuff, and this is measured in flops. So that's like computations per second sort of idea here. And so you can just imagine that as as this goes up, you just need a bigger computer or more time here. And through 2010, we grew, at a certain rate. But after that, when we got into these larger networks and found out just adding more layers and stuff increased their efficiency, we put a lot of resources in, training these long time, spending weeks on very fast computers. About this time, we learned how to use GPUs to do a lot of this training. And a lot of these companies were investing in specialized hardware where they have multiple GPUs training these systems. And this whole idea of machine learning hardware became common. Because training was taking so long, what we found out is we could do something called transfer learning. And so this is kind of what transfer learning does. So let's take VGG 16 as an example. We would train VGG 16 on all of the ImageNet data. I would learn all these filters on how to recognize low-level features, intermediate-level features, and even high-level features. So it would recognize everything from a leopard to a mushroom to a jet here in these features, and certainly learn faces and that sort of stuff. And then we have these fully connected layers that would then try to determine, based on these image features, what the result was. And so what we did, let's say we trained it on ImageNet, but now we wanted, instead of learning on ImageNet, we wanted it to diagnose something like breast cancer from X-ray images. That's not in ImageNet. But what we found is that we could take a pre-trained network here. We could get rid of the top fully connected layers and put new layers here, brand new ones, new softmax, new fully connected layers in their place. And then we could do training and we could lock in all of these low-level features and not change those and just train this top-level network. And then the amount of parameters we're training was a lot less. So we might train 150 million parameters over here and spend weeks doing that. But once we have that, now we can apply it to different places and maybe just train 100,000 parameters here. Because again, this is just a 256 network connected up to whatever it is below. And then this is 256 times 256 connections. And this is probably 100 times 256 connections. So a lot, maybe 1 million connections, but not 150 million connections. So it might be 100 times faster just to train, fine-tune this by adding a new top to this network. That's like when we do the whale database, like in the project this week, this is what you'll be doing. You'll be trying to train the whole thing, and that'll take a long time. You probably will only maybe do that once or twice. And then we'll give you pre-trained models, and you can put in a new top here, and you'll train that much faster there. So you'll be able to train this and try different characteristics out here. Now, and this is a nice little network. We can give you a modern network with 100 layers. And again, only retrain the top 3 layers for that. So that's this transfer learning or fine tuning here. So there's 2 ways of doing this. Now, I used to not cover this that much, but with large language models, this is used now a lot in large language models. So when we get to like ChatGPT and stuff towards the end of the semester, we'll talk about this same sort of stuff. So that's why I'm bringing it, I'm spending a little bit more time on it here. There's 2 ways of doing this. One is fixed weights. You can train this thing, and then you can just fix the weights and train the top. The other one is to fine tune the weights. So maybe you train the network and get all the weights very close, but then you will still train it all, but you'll fine tune it. You won't have to train it as long. Like we find that with the whales often helps identify whale tails, because there are certain features in whale tails that are just more common in whale tails than in other things. But there are often these feature detectors, these layers are already detecting something close to that. So we can just take a VGG or a network that's trained on ImageNet, bring it over here, feed it a bunch of, show it a bunch of images of whale tails, and it will tweak, it'll fine tune these weights. The weights are close, but it'll fine tune them to work just on whales there. So again, sometimes you can fix the weights and only train the top. Sometimes you can add new things and then fine tune other ones. So then I asked, I told you large language models will be this way. And so I asked ChatGPT or asked Bard/Gemini about this. And again, it summarizes it in the same way here. So like it says, a large language model is similar to having a brilliant linguist with vast knowledge of the English language, but lacking expertise in a specific domain. Fine-tuning these large language models works similar to this. We can train it for a specialized task or a specialized thing. So we could train it just to do translation in a certain language, or just to create certain types of output, like marketing copy or scripts here. So you could fine-tune it just to create Broadway musicals or something like that, or code generation in certain languages. And so often we'll take these systems and we'll train them just to generate code for different ways. So that's what we'll be looking at, and we're doing a lot of work in it. I'm just going to show you the preview, this notebook. Like this is the way we're used to doing it now, where we define all these layers here, and we set up the whole network. What we're going to still try that out, but we're going to use these pre-trained networks, and we'll have a whole bunch to choose from. And then we can just pick one of these pre-trained networks. So we can say, give me ResNet 152. It's 152 layers network, pre-trained with the ImageNet database weights. And we won't include the top here for this. And then we'll add our own top. So we'll take that, and we're only adding 3 layers to the network for this. And so our network will actually be very large. Here's the network. There's, I can say, the network has 152 layers in it. All these layers are all pre-trained for us. Layer after layer, 152 of these layers are set up for us. And then this goes on forever. This is just a huge network. This one is. Okay, and then we are just adding onto it at the end here. So there's a total of 58 million parameters here, which will take us forever to train. But again, most of it is fixed. We are only training 595,000 parameters of that. So we're only training a small section of that. So we'll see that next on Thursday when we do this notebook. So, I just want to mention a couple new layers. Not going to go into too detail. One, and again, they're using different. We've talked about max pooling. You remember where we have a 2x2 filter and we find the maximum. There's also something called average pooling, and some of these advanced networks might use average pooling rather than max pooling here. Also, there's something called global average pooling here, which applies this averaging to the whole image here. So sometimes at the end of our image, we'll do a flatten where we're going from a 2D image to a 1D image. We'll flatten it, but that still generates a lot of our layers or connections are often right at this level. Global average pooling is a way of flattening by just seeing if there are features on our final image. It often leads at much smaller networks here. So we've talked about dropouts. There's a special dropout for convolutional layers called a spatial 2D dropout. So it's optimized for these convolutional layers. We haven't mentioned normalization, but a lot of times in these networks, these deep networks, the activations get bigger and bigger or smaller and smaller, stuff like that. Batch normalization is a layer that kind of rebalances the inputs to the next layer, so they average at 0 or they're within some range. So again, sometimes to manage these large networks, there's batch normalization in here. And then another layer, like the inception stuff, we have a layer called concatenation, which will combine different inputs together and concatenate them in a certain way. Again, I'm not going to really go into these. I just want you to know that sometimes when you see these, so like if we're looking at one of these big networks that's already predefined, we'll see, like here's a batch normalization layer. And here's another batch normalization. So it'll have these layers built into it here. So I just wanted you to know that there are some other layers built into these ones. Okay, so that's what we'll be looking at is some of these large networks. And see what they do. Okay, now I think I'm going to stop talking and let you all do some work here. So I want you to go to, what we're going to do is go to Unit 6, scroll down. We're going to talk about machine learning APIs and bounding boxes. So in machine learning APIs, so there are these pre-trained networks, but also some of the companies have whole systems set up to do this recognition so that you don't even have to do much at all. So if you're creating, like, I don't know if you've seen any of the smart stop signs around stoplights around town. They have a little camera on top of them. They recognize cars. So if you just need a system like that to put in your traffic light system to recognize cars, you don't have to train it. You can just grab one of these pre-trained models and do it. So Amazon has their recognition model, spelled, of course, some Amazon way. Microsoft has their vision service, and Google has something called Vertex AI, and inside Vertex AI is something called Vision here. So I want you to do a little research on one of those. I also want to look at some other ways of doing image recognition. Rather than just saying that's a cat or a dog, we wanted to be like, look at an image and say, okay, this part is a dog, this part is a bike, this part is a car. So put bounding boxes around objects and detect multiple objects here. We get to do the sea turtles database as part of this. The other thing is image segmentation. So rather than rounding bounding boxes, we'll just look at actual pixels and say these pixels are part of a person, these pixels are part of a car, sort of stuff. And that introduces a new network architecture called UNet here. And again, with all of these different outputs, if we're not just doing classification, all these things have to have a loss function. How do we figure out how far off the network's output is from the actual output so we can learn, so the network can learn and change the weights? So we look at 3 different loss functions here. Okay, so here's what we're going to do. We're going to, at the top of this is this describe, image, and quote activity. We want you to do that. There are 11 topics down below here. We need a description. I need 2 images and 2 quotes for each topic here. So a description, 2 images, and 2 quotes for each topic. And that's what you're going to be working on. We'll have you work on that, fill in these things, and then at the end, we'll just go around and kind of have someone summarize something. So if you put something in, towards the end, someone will say, okay, we're doing YOLO. Someone tell me about one of the images. And if you put one of the images in, you'll volunteer happily to share that with the class here. So now I've just randomly, well, I put in everyone's names in here, and you're in multiple places here. Most people have 3 places. Some people won't have 3 places. So find yourself. So like Vince isn't here, but if Vince were here, he would start by, oh, this should actually be, let me change this description. Describe. Okay, the first thing is to describe it. So Vince would look up YOLO and try to do a description of it. Vince and Henry would work together on that stuff. And the images for YOLO, Stefan and Joe would work on those and put in here. And the quotes, Reese and Addison would do the quotes. So again, like Addison, you want to find a quote for YOLO. So down here, topic 2, a quote, you want to put in a quote there. Okay. Max, over there, Max, you are listed in the loss function for this IOU loss function. Describe that. So again, you want to find out something about it. That's topic 7. You're going to go down to topic 7 and put in a description. But Miles, who is behind you, is also helping. So you can decide, maybe you want to do it and have Miles proofread it or tweak it afterwards. Maybe you want to do 2 descriptions and murder. I don't know. Do it however you want there. So there's 2 people assigned to each, the describe, the image, and the quotes for all the things. Research it, put it in here. Feel free to use AI if you want to use Bard or, ChatGPT to help you with some of this stuff. Feel good. I want the quote to come from a real person or an actual article, not necessarily an AI for that. Questions on this? All right, I think you've done this sort of activity before, right? Maybe not in a computer classroom like this, but you've done the break into groups, research something to mine sort of stuff. Maybe. So, okay, find your names. That's just up. If you get done, I'm going to identify some places that are missing and we'll fill in some missing blanks in here too. So I'll let you get to work. Let me stop.